Okay. Okay. So we're going to do a screencast of the third lecture. So there's a review of finding reactions about the frameworks and introducing method joints. So currently, when we got to lecture 3, what should have been kind of embedded, hopefully, was what we need to do to a resultant force and how we can then split that up into force components. We're working in just 2 dimensions, so we've got this force going in this arbitrary direction with maybe some angle against a horizontal, for example, and I can then split that force component up into a horizontal component, so an Fx term, which will be based upon the total force, and we'll take the total force, treat that as a magnitude, and that would be times by cos theta, and then the Fy term will be the total force times by sine theta. So yeah, so we covered that as part of the primer revision week 1. There's a couple of primers left if you want to have a look at them. It takes you through the basic sort of like trig that we need, the Pythagoras, and things like sine and cos and tan. So this is the important one that we can break up. So let's imagine this was a 10 Newton force, and that you'd need to break this up into a force in the x direction and a force in the y direction. So we then have to remind ourselves of the basic trig. So if we were looking for the force in the x direction, we'd think, okay, well, that's the adjacent. If we've got this angle here, 30 degrees, and the nice long line that's always at a kind of diagonal, well, not always, but you know, it's the long one, that's forming part of this right angle triangle, and that's going to be the hypotenuse. And so that is going to give me the cos 30 equals the adjacent length divided by the hypotenuse length. So we are looking for the equivalent of the adjacent in the horizontal direction. If the hypotenuse was equal to 10, we could rewrite this as what we got, adjacent divided by hypotenuse. So adjacent divided by hypotenuse, fx divided by 10 equals cos 30. Put cos 30 in your calculator, you know. Don't be a hero, use your calculator. So put cos 30 into your calculator, times it by 10, and then you end up with that we've got the equivalent of 8.66 newtons going along the horizontal. So the things that we've covered so far up to lecture 3 is the concept of statics, equations of static equilibrium, so that we're summing up forces in the x direction, we're summing up forces in the y direction, and we're taking moments, and we're going to take moments at anywhere we like, so some logical place that we choose on the framework usually. That's convenient to measure distances. Fine, so typically that will be a joint. Finally, we can work out the reactions at support, so we'll go over that again. Introduce the idea of concentrated and uniform distributed loads on beams. So this kind of problem is example 1, page 18. Probably there is a video of this, but these are sort of things that we should be able to knock off quite straightforward. And the issue really is what we do about these forces that's pushing against the framework at these odd locations. To tackle a problem like this, what you want to do is you want to think in terms of that there's almost like a beam here in the x direction, and then another one in the y direction. And what you want to do is you take your forces. Let's go for a nice yellow. No, my colour didn't change. There we go. So this force here, and this force here, this force here. Now what we're looking for is we're looking for the turning force, and for sake of argument, I'm going to do this around this pivot. So I could try and work out from this pivot position going up to this force how I'm going to get a kind of perpendicular line of action. Now the easiest way of doing this is to use these two lines, this x axis and this y axis, and then to say where these forces are, let their line of action move such that they're going to hit either the x or the y axis or go through the pivot. So this 2 kilonewtons here, we're going to let it move until it hits either the x or the y axis, and it ends up hitting the x axis here. And then we're going to measure the distance, and we're going to create the turning moment. So we've got 2 kilonewtons which we're bringing down to here. What's the distance from here to here? Well, it's going to be half of 5, so that's be 2.5, and we're going to do the same thing for all the other forces. So bring this one down, so it hits there, so we've got 2 kilonewtons down there. Bring this one down, so it hits there, so we've got 2 kilonewtons hitting there. Okay, this one's interesting because its line of action is like this. So this time we imagine we're in a car and we're going to hit the reverse. So the line of action can go either direction, that way or that way. Okay, so we'll get rid of that one and then bring this one back, and it hits there. And that's got 3 kilonewtons. So now you can see what we're going to do to sum up the moments to then work out what this reaction is. We would have m sum up the moments at A, and we'll go around clockwise. So the first one that I see is this 3 kilonewtons, and I can clearly see its distance away from that y-axis there. So you've got 3 times 3. Okay, so that's the first one done. Next one here is I've got 2 kilonewtons. It's a distance of 2.5, so that's going to be plus 2 times 2.5. Next one will be this one here, so that's going to be 5. And it's at a distance 5 away, so 5 times 5. This one here is going to be 2. Notice these are all positive moments. 2, distance of 7.5 away. This one here is going to be 5 kilonewtons, and it's a distance of 10 meters away from the pivot. This one here is going to be, what, 12.5 away, so we've got 2 times 12.5. And finally we get to this one here. Now this is a reaction force, and it's going in the opposite direction, so we'll call this minus 15 RBY equals 0. So I'm going to put all this in my calculator and find out what RBY is. So RBY equals, so I've got 3 times 3 plus 2 times 2.5 plus 5 times 5 plus 2 times 7.5 plus 5 times 10 plus 2 times 12.5, and divide that by 15, and I get 8.6 kilonewtons. And what you could do is you could either take moments at B, or you could sum up your forces in the y direction to find out what RAY is going to be. So let's sum them up. So the first reaction we're going to have is this one here, so that's going to be the RAY equals, so that's going to go upwards. So we've got what? We've got RAY going upwards. I've then got 2 kilonewtons coming downwards, 5 kilonewtons coming downwards, another 2 newtons coming downwards, another 5 coming downwards, another 2 coming downwards, and then we've got this RBY term, and that's going upwards, so that will be plus, and that's all got to equal 0. So make that 7.4, so RAY equals 7.4. Right, and the only other thing is to work out what the reaction is at the hinge in the horizontal direction. And there's only one force which was originally there, but I moved it back here. And so you could sum up the forces in the horizontal direction. So I would have a force going in this direction, RAX, plus 3 equals 0, so therefore RAX equals minus 3 kilonewtons. So I found all the reaction terms there for that kind of problem. So many examples there, and I refer you to page 18, example 1, and that you'll find videos either by Arnold or me taking you through these type of problems. So when I did that problem, in effect, I was really not interested in the framework inside, was I? That could have been any old junk there. You know, all I did was I took my forces and moved them to positions that I could then measure them conveniently. So this one here, all the way back there. So that's all I was doing. So and I was taking into account that the hinge has horizontal and vertical reactions, and that this one had only a vertical reaction. Okay, so that's all the stuff that we should be okay about. And here we have the final solution. So notice the final solution is giving me the 7.4, the 8.6. I found those, and just for convenience sake, I've flipped the 3 kilonewtons to be pointing the opposite direction, so I can get rid of the minus sign. So I found that I decided that I had minus 3 kilonewtons going in that direction. But in my final solution, I'm going to flip it and express the 3 kilonewtons going in the opposite direction. Both are valid and are acceptable. So we have had external loads on our framework, and then we've got these external reactions. So what the framework's not moving, so we're applying the basic principle that sum of the forces must equal 0 because my thing isn't moving. So no accelerator, so it's not accelerating. Okay. Now that starts making us think, well, what could be going on inside these members? If I'm pushing down these members, what could be happening inside these members? Could they be being pulled apart or squashed together? And if so, how much stress, how much tension there is when I pull them apart, and how much stress, compressive stress, when I try and squash them together? There's many more examples there that you can look at for working out the reactions. So you can see example on page 18, page 20, page 22, and the work solution on page 23. And all of these will have been videoed either by me or by Arnold. Okay, I'm going to leave this problem as a point where you might want to pause the video and give it a go yourself. So see if you can find the reaction RBY. So pause, and then we'll try doing the solution. So pause now. Okay, so hopefully you've had a crack and see if you can work out the solution. I only asked you to find the value RBY here. So what are we going to do? So we've got these 20 kilonewtons sort of in space. Let's create a fake line there and imagine that that can be pulled back to this point here, and then I can work out what that turning moment is going to cause. So if this is my hinge where we've got RAX and RAY going in those directions, since the question only asks us for RBY, it makes sense then to take moments at that pivot there, and then we're going to get rid of these two terms because the distance times the forces is going to be 0. So when I sum up my moments at A, I'll have 20 times by 1.5 when we're going in the clockwise sense, and then take away what's the distance from here to here, going in the opposite sense. So that will be 2 RBY equals 0. So RBY is going to be 10 times 1.5, 15. So if you've got 15 kilonewtons, give yourself a pat on the back. This is quite a straightforward problem, so you could quickly find the other terms without any problems. Sum up the forces in the x direction. And then you've got RAX going in that direction plus 20 equals 0. So RAX equals minus 20. And then you could sum up the forces in the y direction. So we got RAY going in that direction, plus RBY going in that direction, and I can't see anything else. So my RAY is going to equal minus RBY, so therefore it'll be minus 15 kilonewtons. Okay. So that was a revision of finding reactions at points, and there's another problem here that you could try, where I've now put on two forces. Okay, so this one here adds on this additional force of this 10 kilonewtons, so you want to pull it back to that position, and this one here, pull it back and measure it at that point there. So you've got your 20 and you've got your 10, and then you measure your distances, so 1.5 and 1. Okay, and if you want to give that a go, then the solution is RAX equals minus 20, RAY equals minus 10, and then RBY equals 20. So give that one a go if you like. So let's move on to looking not so much the framework and then kind of considering the whole body of the framework, but actually looking inside the framework and how it's constructed with these various members. These are given various names. I don't know them off the top of my head. One of these, for example, will be a Pratt, and the other one will be a Howe framework structure. And they tend, you notice, to form triangles, and that's because a triangle is deterministic in terms of its movement. So it can't move. If I fix one point in the triangle and the other point, then this triangle is not going to move. Whereas if you took, say, a square, you could imagine you could fix this point, and but we could then apply a force here, and then the whole thing will kind of shear, as it were. So some nice examples, some of them using triangles here, for example. You can see some triangles there appearing, and it's because of this this strong formation. There you go, got a lot of nice triangles appearing there, and these are going to be called Hoxingerians shapes, so that it's kind of like a 3D type triangle setup you got there. So, some definitions for you. A truss is a framework consisting of members, and these members can be bars, struts or ties, and they can be used as a model for most structures, in particular for things like bridges and maybe the basic underlying framework in, say, an airplane. Okay, a pin joint structure, well, that's a special form of truss structure consisting of members with only end joints. So that's a bit interesting. So previously a truss structure is something where we've got basically beams all connected together. Typically they're going to probably form triangles in some form. Well, the pin joint is when we're looking at our two members coming together, we're going to put a pin in there. Okay, so that pin in principle can kind of move around at the end of the joint. So these joints can be treated in effect as hinges, and what we do with these joints is we could stick them onto maybe a surface so that they can only go in a certain direction, or that we could kind of glue them so they can only sort of move around in a certain direction. And this is this term called determinacy. So that's whether if my joints, in effect I've kind of restrained my joints in such a way that they, if I apply some force, they won't all kind of collapse and move or whatever. Now, the things that form my truss, so my members, so typically I would have maybe 3 bars come together, and they would be depends how you apply the force, but they'd probably have 2 struts at the top and 1 tie along the bottom. And a tie is in effect like a bit of string, a bit of cable. It's something they're trying to pull apart. So it doesn't really make sense to have a big heavy bar that you're trying to pull apart, when a bit of cable, metal cable, would be much lighter and do the job just as effectively. However, a piece of string would not be very good when you're trying to squash the member together. In that case, you want to have something called a strut, and examples of struts would be posts, poles, girders, some sort of solid roof rafter or something like that. So here on Clifton's suspension bridge, we've got some nice big struts. And what would these be? Well, these would be sort of solid members. Okay, possibly. Actually, they could be ties, couldn't they? So these are going to be being pulled apart, and then you've got ties coming down to our platform, and well, because we've got cars driving across, we're going to have a platform at the bottom. But the 2 important ones there is this strut here, and the tie here. Okay. So the load, if you like, that's on the bridge, is pulling down on the tie. The tie is now pulling down on here, and what I want to do is then get that being pulled down and take the force off in this direction. So we're pulling down in these 2 directions, and then we're squashing our big member in between, and so this will have to be something solid as it's trying to get squashed by all that pulling apart. So if I've got, just looking at the members, I could say that I've got a member which I might want to pull apart, and that's in tension, or I've got a member that I might want to squash together, and that's going to be in compression. I could imagine that we're going to cut this member in half, and there's still therefore going to be, if I look on the outside, a force going off in this direction and a force going off in that direction. Now let's go back and think about your weight hanging off a string problem. So you've come across this quite a few times. So we've got a weight, got a string, and we know string has tension in it, and we know the weight wants to go downwards. So what's the tension, the weight, that's mg. What is the tension that's going to be in the string? Well, that's straightforward to solve, because you can see that the tension's going up, the weight force is going down, so we have tension equals mg. Okay. We have just done the first example of method of joints, because this problem that was given at school is not strictly makes sense, really. What you're actually solving is we've got a piece of string attached to the ceiling. We've got the weight coming down here, mg, and then we've got a reaction force here at the hinge. I'll call that R hinge. That's the problem we're actually solving. What's going on inside the string, we don't know. So what they've done, without telling you, is that they've done an example of method of joints where they've taken an imaginary cut through the string and then said, well, if you took this part of the diagram away, there must be some kind of internal force that's balancing this external force at my cut, because my string's not moving. Okay. Now, I'm going to define, because this is going to be a tension force, I'm going to define that my force is going to be pointing away, if you like, my joint. So the string goes around a little hole in this weight, and that's going to be in effect my joint. So this is an external force here, and we've taken an imaginary cut through the string and we've exposed an internal force, and it turns out that the internal force equals a positive mg value. Okay. So what else do we have going on in the string? So we've got this internal force, and you could say just outside of that cut that I've done, there's another internal force which is balancing. So all the way along the string I can make cuts, and then either side of my cut I'm going to have this tension all balancing all the way through the string, equal and opposite, so they don't add to any sort of resultant force. Okay, and these are, as I said, a different type of force than the external force, but the imaginary cut exposes this internal force, and it tells us by our definition that we're going to call it a positive mg force. What happens if we did the reverse? Well, we had some kind of bar which was standing on the earth. The bar didn't weigh too much, and we applied a load on the bar, so 12 newtons. Well, that bar would be pushing into the ground, and there would be an equal and opposite reaction. So 12 newtons would be going off in that direction. So what I just did with the string, now let's do with the bar. Let's do a method of joints, where my joint is where this force is going to be applied, so it's kind of like there. So I'm going to imagine that there's some force inside my bar. Let's call this force compressive force F, which is going wherever I make that cut, there will be these forces equal and opposite all the way through the bar. And now we're going to take this away and imagine that we can solve this as a free body diagram problem. So we've got this 12 newtons pushing in this direction, by definition, I don't really know which way to point it, I will have my force pointing away from this joint. So that's my F. And now I'm going to solve that. Well, in this case, I'm going to sum up my forces in the y direction. I define downwards as being positive. And so that gives me F plus 12 equals 0. So F equals minus 12 newtons. So the value that's inside the bar is the same force that's being applied outside the bar, which was the same for our string, as it were, but with the string we had the mass pulling the rope, and it turns out the tension we're saying inside the string is the same as that weight. So they seem the same, but this time I ended up with a minus here, and I'm going to take that as a convention, because I know this thing here is an example of something being compressed. So I'm going to say, as a hypothesis, if I get minus internal forces, it's in compression, and if I get a positive force, it's in tension. And we find that that works even when we get into more complicated framework scenarios. Okay, so that's the important concept for a method of joints, that there's these external forces being applied to members, and that these members have forces inside them where we're going to define them wherever that cut might be, that we have this equal and opposite force inside the member as I try to apply some force outside the member. The forces inside the member have to travel in the direction along the member only. That's the only way they can move, because where I take that cut, you can see that force is going to be moving perpendicular to those possible ways, the million ways I could take the cut through the member. So the concept with the method of joints is that a joint can be analysed attached to one of the members for the internal force to be found. Okay. So we are going to be looking for what the internal forces are, where we're going to pick on a particular joint and we're going to take an imaginary cut around that joint. Each joint acts as if it's in equilibrium. So the external forces applied to the joint and the internal forces that we're exposing by cutting around those members, all those forces must be in equilibrium so that that joint can't move. Next, we're going to take a cut so that we're only going to be cutting through one member or two members. My examples here, I did cuts through one members. In actual fact, when we come to frameworks, it's always going to be cutting through two members. So we're going to choose cutting through two members. Sometimes when I'm at some point in the framework, I could go to another joint and I'd end up cutting through maybe 3 or 4 members, in which case that's probably not the joint you should be going to. You should be going to a different joint because you're introducing too many unknowns. Each time we are at a joint, we're going to draw a free body diagram of interest, and we're going to show all the internal forces and all the external forces acting on that joint. And it's a good practice to first draw your first free body diagram, just showing algebraic representations of those forces. So we've looked at this kind of framework problem. How can we go about applying a method of joints to something like that? So we're looking for the forces that are inside that framework, and we're going to define our forces as if by assumption, a bit like I've done with my string and my strut there, that those forces are always going to be pointing away from my supposedly contact point, my joint point, where I'm applying the external force. Okay, so they're pointing away from that. So that structure, that framework that we had, what we can do is we can imagine we've got all these internal forces going on in each member. So we've got an internal force here, an internal force here. Now where they exactly lie, it all depends on how I'm going to make the cut. So if I make a cut around here, so that internal force will kind of come up to that cut, and that internal force will come up to that cut. Okay, so we've now got these two forces here, this one here and this one here, which are the external forces. We're going to do this method of joints thing where we're cutting through those members, and then we're going to be exposing these things here, which are the internal forces that are being applied at this joint A. So you notice on that framework what I decided to do was, for each member I had the forces in each bar pointing away from a joint. So if I'm pulling my member apart, the internal forces will be going the opposite direction. They'll be going that way. So if I'm pulling them, internal forces will be going that way. So that would mean if they're going in this direction, they're in tensile. They're being pulled apart. Okay, and we're going to assume that's true for all the members. So what we're then going to do is then calculate what those internal forces are, and if they turn out to be negative, i.e. they want to be pointing the opposite way, we can say, that's good. That force must be in compression. So we're going to assume that all the internal forces are tensile, meaning that they're all pointing away from the joint. And if we end up with a negative value when we do our calculations, then we know that those forces are an example of something in compression. So here's me pulling this member apart, and the forces are pointing away from the joint. So we've got to imagine our joints are here and here. And you can see that those forces there seem to be pointing inwards of the member. If, however, we were squashing the member, what would end up happening is that we would have internal forces trying to oppose that squashing, and those internal forces would be pointing away or pointing towards the joints. So we would actually be finding values which are pointing away from the joints, but they would have a negative value. So in summary, method of joints is all about taking your free body structure of your framework and then finding a joint which only has two members, and you're going to start there and you're going to make a cut around that joint and then say, I've exposed those two internal forces, and if there's any external forces at that joint, then you include them in your new sort of sub free body diagram. Those forces where you've cut through the members, you've exposed their forces, we say that their forces are going to be going in the direction of the members, and we also say that they're going to be going away from the joint. We can then simply just resolve things in the x and the y directions. We've got two unknown forces here, these two unknown internal forces. We've got two directions to work with, so therefore we've got enough to solve them. And then you carry on around your framework until you find all the values you're looking for. So I could start here, for example, because I could be making a cut through these two members, or I could start at this point here. because I'm cutting through two members. I can't start anywhere else. I can't start here because I would be cutting through 1, 2, 3 members. So that's 3 unknowns. So A and B are both possible starting points if I was looking, for example, the AD force or the BE force. Let's just take the look at applying the method of joints at joint A. So going to cut around joint A. So now I'm imagining that I'm going to draw a sub piece of diagram of my free body diagram just at that section A there. So what's convenient to do, makes more sense, is to take just that bit of framework out and just examine it further. So then you might want to start working out what's that angle here, or what's this angle here, call that gamma. So those are the sort of things that you might want to do, going back to your framework. And if you had those values, then what could you do next? So let's say we knew those angles, we looked at the framework. Well, then you could resolve, and you would call this method of joints, so you call it MOJ. Now, when you do method of joints, you're going to resolve forces in the x direction, and you're going to resolve forces in the y direction. Which you choose to go first is up to you. Okay, you don't have to do the x direction first just because it's x. Look at your diagram, and in fact you don't even have that thing doesn't have to necessarily point up. You could point down if it was easier. Look at the diagram and say to yourself, if I resolve in the x direction, how many unknowns am I going to pick up? Well, if I resolve in the x direction, I'm going to have AC going off in the x direction, then I'm going to have AD swinging through cos theta, and that going off in the x direction. So I'm going to have 2 unknowns. What if I resolved in the y direction? Well, if I resolve in the y direction, AC is perpendicular to it, but AD would swing through this angle gamma, and that will be picked up. So you choose the one, well that's only going to pick, if you've got that option, you're going to choose resolving your forces in a direction where we're only going to pick up one ideally unknown. So if I was doing that, I was going to resolve forces in the y direction. So I would then have AD cos gamma plus 7.4 equals 0. Now I would need to know what that value is, but that gives me AD equals minus 7.4 divided by cos gamma. Now I don't really know what those angles are, but this result is telling me something kind of interesting straight away, because it's telling me I know that cos theta is going to be somewhere between 0 and 1. So it's going to be a positive number, and so it's telling me that AD is going to be a member that's in compression. Okay, if we now did the other thing, so that's even without working out what cos gamma is then. So once we did that, we would then go and resolve forces in the x direction. Not planning to solve this. And in that case I would then have AD needs to swing through the theta this time, so it's AD cos theta plus AC, and then we've got minus 3 going in that direction. So previously we would have found that result, and so then we could find AC equals 3, AD minus AD cos theta. So that would give me what? Well, I could substitute that thing up there. So 3 plus 7.4 cos theta divided by cos gamma. Okay, again, I'm not working out the angles, but looking at the values that we got there, what can we see about AC? Well, first of all, we can see that AC is going to be in tension, because it's going to give me a positive number. Doesn't really matter, because my what my cos theta and my cos gamma is going to be. Possibly it's going to give me a value that's bigger, possibly not, than the AD. But you get the basic idea then, how to do method of joints. Now once we've done the AD value and we've worked out what that is, we're then in a position to go and move on to another joint. If say I only worked out AD, the only joint that I could go to would be, actually it doesn't really matter even if I worked out this joint here, thinking about it. So if I worked out what that joint was there, I couldn't move on to this joint here. Why? Because I know what that value is, but I don't know what that value is, I don't know what that value is, and I don't know what that value is. So I'll be cutting through three unknowns. So the only joint I can move when I start from this joint is to move up to this joint here, because I know what AD is, and then I'm going to take a mirror image of AD and then shove that value into AD and then point it in the opposite direction. And then I can have an unknown here and an unknown here. So when I cut through around this joint, even though AD looks like it's an unknown, we did previously solve it. Note that if AD, I think AD was minus, wasn't it? AD is a negative value. So AD is a negative value pointing this way, and AD is going to be a negative value pointing this way. It's not absolute directions, it's relative directions to where the joint is. Okay. So then we could go around the framework and find all the internal forces in my framework using this method of section approach. Okay, so let's work on this problem here. So it's the first problem that we looked at, where we found what the reactions were. So you previously paused your video and you found that RBY equals 15 kilonewtons, RAY equals minus 15 kilonewtons, and we've got my RAX equals minus 20 kilonewtons. So we'll call this joint C, and we want to find all the internal forces. I will do positive and use negative value. Okay, so they are my external forces being applied. And I'm going to start off doing method of joints. I could do method of joints actually. This is an interesting one because I could do method of joints anywhere I wanted. I could do it A, B or C. So it's similar to the previous problem. I will do method of joints around A. So method of joints at A. So the first thing I do is I form a new diagram showing these internal forces. So I've got an internal force AB, internal force AC. We've got minus 20 coming in from left to right, and then we've got minus 15 coming in bottom on top. Okay. If I wanted to, I could make these arrows point in the opposite direction, make them positive. Right. So, what's the other thing you want to do is you want to do a little bit of geometry when you're doing this sort of analysis. So we've got 1 meter, 1.5 meter, and we're calling that a theta. So that tells me that cos theta equals 1 divided by, actually I need to work out what that length is then. So that is going to be what's the hypotenuse? So that is root 13 over 2. So that's 1 over root 13 over 2, so the 2 will end up on top. So if we wanted to work with irrational numbers, not very pretty is it? Let's start again. That's going to be 2 divided by root 13. If you prefer, you could actually find out what that feature is and then carry on like that. Other stuff, let's work out what sine theta is going to be. So that's going to be the opposite. So 1.5 times 2 over root 13. So that's going to be 3 over root 13. I'm going to use these cos's and sines to do my problem. So you can put in not too much, but some geometry information into your free body diagram there. What way should I resolve my forces? Well, it makes sense to resolve forces in the y direction. So I'm going to pick out the AC. So I'm going to swing through this angle here, and it's not theta, so not swinging through theta is a sin. So we're using a sine. So that's going to give me AC sine theta, and then we got minus 15 pointing upwards, so minus 15 equals 0. So that gives me AC equals 15 divided by sine theta. Sine theta is this thing here, so that gives me 15 3 root 13. So that's going to go 5 root 13. So that's found the AC one. I could then put my calculator and get a real number. So what's that? 5 times root 13. So that equals 18.03 kilonewtons, and it's a positive number, so it's going to be in tension. Okay, now let's find the other force, the AB force, and we'll find that by resolving in the x direction. And what we got now? So we've got minus 20 going in the x direction, left-right direction, plus AC cos theta. I've swung through theta this time, plus AB equals 0. We're looking for AB, so let's rewrite this. AB equals 20. Take away AC cos theta. 20 take away AC, and we found what AC is. I'm going to use this this irrational number here, and we're going to use cos theta there. So the AC value is 5 root 13, and the cos theta is 2 root 13. So the root 13s will cancel. 2 times 5 equals 10, so we end up with a nice number of 10. So AB equals 10. AB is also going to be a positive, so that will also be in tension. Okay, got a blank page here, so now let's go and do method of joints at B. We're going to do a cut through here, label up the external force, 15, and when we do the cut we'll expose the AB term and the BC term, and what we're looking for is the BC term. So method of joints means this angle here theta will be this angle here theta. So you really want to draw a new diagram. BC, AB, put that angle in there, theta, 15 is coming upwards. Since we've already worked out AB, we're only looking for BC. What's the logical thing to do? Well, resolve forces in the y direction to find it. So resolve forces in the y direction. So that means not swinging through theta, so that's a sin. So we want to use sine. So we got BC points upwards, provided I swing it through a sin. And then we've got 15 going upwards, and nothing else. So BC equals minus 15 divided by sine theta. Let's look back. See what sine theta is. That's 3 over root 13. Whoops. So we've got 15 divided by 3. We end up with a 5. And that's the same value that we had before, but this time it's negative. So minus 18.03 kilonewtons. And this time it's a minus value, so we highlight that we know that that is in compression. So we put a C there. So BC is in compression. Does that all kind of make sense? So if I'm pushing here, I'm going to be pushing into this joint. So this bar is probably compression. I'm trying to push this bar away from this hinge. So yeah, that's probably in tension. And I'm trying to push the framework left to right. So the AB, yes, that's probably in tension. So those values, do a kind of quick logical check. See if that seems a plausible answer. So finally, watch out. It's very easy to mix up the concept of an internal force, which is happening inside the bar, and the external force, because with the method of joints we've cut through them and we've exposed those internal forces to you, and we're doing calculations all over the place which are involving internal forces and external forces, and we're saying that they're going to have to balance. But don't forget, they are different things. The external forces are the things that are being applied to the body. The internal forces is what's being experienced inside the body. You could have a go at this. So this would be a good time to try and pause the lecture and see if you can solve this one. So pause. Okay, so hopefully you had a crack at that. And here's the solution. So since we're only looking for the AB, we're only going to bother resolving the forces in the y direction. So I decided to use cos theta, not sine theta. So I worked out what that angle was going to be. Then I swung through my AB so that it pointed vertically. So I swung it through a 60 degrees, so AB cos theta. My 10 is going downwards, so it's going to be minus 10. So you should have ended up with AB cos theta equals 10. AB equals 10 divided by cos theta. Then use your calculator to find out what cos 60 is. And so we then find that we got AB equals 20 kilonewtons. Okay. Thank you for your attention.